Hi, this is Peter with CalcBook, and today we're going to be looking at a roof purlin design, and we're going to be doing it using metric units. So just a quick overview of our purlin design here. We are going to be using AIC specification Chapter F for flexure design. We'll use Chapter G for shear design, and then we'll be using partially Chapter J for the connection design for the bolts and weld capacity and stuff like that. But then we'll also be referencing the AISC manual part 10, which talks about single plate shear connections. So let's take a look at our problem statement today. We have a floor plan here with 6 meter long channels. We're going to be using a C310 and then designing for the most economical shape. So we have purlins spaced at 2 meters or 2,000 millimeters on center, and our top flange is continuously braced. Our area loading, right, our floor loading, we have a dead load of 2.5 kilopascals and then a live load of 5 kilopascals, and that converts down to 5 kilonewtons per meter and 10 kilonewtons per meter for our distributed load on the beam, considering the spacing of the purlins. So our design checks for this system, right, we are going to be looking at the beam, bending, shear, and deflection, and then based on that, we'll pick the most economical shape for our C310. And then we'll also be doing a single plate shear tab connection with the end reaction loads from our purlin. So let's go ahead and open up CalcBook and we'll get started on the design. All right, we've got CalcBook open now, so we go and click into our 15th edition for the steel design. We'll click into our member design. We'll start with the purlin. And then we'll go ahead and click on our major axis flexure and shear, and then we'll make sure we toggle over to metric and click confirm. So let's go ahead and select our shape type, right? We're going to be using a channel. And then we said we're going to want to select the most economical 310, so let's just go down to the lightest weight 310 here, and that's going to be a 310 by 30.8. So we've got all of that information loaded up. And then we can go to our beam loading tab, right? So we have a beam length of 6 meters. Our analysis location for shear is going to be at 0 or 6 because it's simply supported. And then our moment is going to be 3, and deflection also 3 meters. So for our dead load, right, we want to apply a uniform load of 5 kilonewtons per meter. So just set that to 5. And then for our live load, right, we also have another uniform load, and we want to set that to 10 kilonewtons per meter. And then we can switch our load combination here so we can just visually see the shear and moment and flexure diagrams, and and deflection diagram. And that all looks good. And we've got our loading summary. So now we can go back to, or go start into our deflection design, right? So we've got a 0.92 deflection for our total, so our dead plus live total deflection. So that is okay. We can also, update our limits if we wanted something different based on our design criteria. If we go to our flexure design, right, we want to enter in our bracing configuration, and we said this is a fully braced top flange for the compression flange, so that is okay as is. And it does look like we are about 7% over, right? And since we are fully braced here, it's just going to be based on the plastic moment, so just our Fy times Z, and that gets us our moment capacity, right? For our lateral torsional buckling, it does not apply because it is braced, so the unbraced length is 0. So we are slightly over here, so let's quickly check our shear design before we go change our member. And our shear design is okay, so we are good to go there. We just need to update our beam, so let's go to the next heaviest shape. So we are at a 30.8, let's go to a 37, and we'll go back to our flexure design, and that works at 0.94. So before we leave this module, right, we do want to just take note of our shear reaction, right, because we're going to be designing a single plate shear tab right after this. So let's take a look at our LRFD ultimate load here of 67.31 kilonewtons. So that's 67.31, and we'll just keep that, and then when we get to our single plate here in a second, we will use that information for our design. So let's go ahead and close this out. We'll go back to our main menu, and we can click into our 15th edition again and go to our connection design this time, and click on our single plate shear tab, and then switch this over to metric and hit continue. Okay, so let's go ahead and first enter in our demand, right? We said we already had the ultimate load, so we don't need to use our load combinations. We'll select none there, and we'll just enter in our ultimate load here of 67.31 kilonewtons. And then we can go to our capacity tab here and start selecting some of our design information. So we're just going to be looking at a bearing type connection. and we will not be concerned with bolt hole deformations. And then we can go ahead and select our nominal diameter of the bolt. So let's see if we can get away with an M20 bolt and see where that puts us. And then we need to increase the size of our bolt hole, so we can do maybe 23 millimeters. And looks like we can get away with 2 bolts here at a 0.92, or we could increase this, to 3 bolts just to have a little bit more cushion there, or maybe we could decrease the size here to an M18, something like that. But we have a little bit of capacity here to play with, so we're okay there. So we're going to leave our connection geometry where it is. We have 3-inch bolt spacing. Our eccentricity, that A dimension is 75 millimeters, and our spacing is 75 millimeters. And then leave our edge distances at 40 millimeters. Our thicknesses, we can leave that as is. It looks like it's okay where it is right now. And then we can go ahead and step through our calculations, right? So the first thing we need to do here is calculate the actual shear on the bolts due to eccentricity, right? Because we are eccentric here, there's going to be some horizontal components with the reaction force. So I need to calculate our polar moment of inertia of the bolt group. And then we calculate that horizontal component due to the vertical force. So this is sort of what we're calculating here, right? And we get sort of our resultant force on the highest loaded bolt, which is going to be that outside bolt. So we get a resultant force of 40.45 kilonewtons. That's on a single bolt. And then from there, we can go through and check all of our different failure modes for the bolt calculation. And we've done this before in previous videos, so we won't go through each one of these, but we have our shear strength of the weld, our shear strength of the bolt, our bearing capacity of bolt holes, tear out capacity of bolt holes, and then our shear yielding and shear rupture of the plate itself, and then our block shear of the plate for the bolt holes. So that is a roof purlin member design and a single plate shear tab design in CalcBook. We hope you enjoyed the video. If you have questions or suggestions for other videos, please let us know in the comments below, and we'll see you next time.